Hello and welcome to the Qubit Guy podcast, brought to you by Classiq, the quantum algorithm design company. My name is Yuval, and my guest today is Rob Hayes, CEO of Atom Computing. Rob and I discussed the uniqueness of atom-based approaches, their go-to-market strategy, his view on diversity in the quantum workforce, and much more. We hope you enjoyed this episode. Please let us know how we did by emailing hello@classiq.io. That's hello@classiq.io. Hello, Rob, and thanks for joining me today.
Hi, Yuval. Nice to meet you, and glad to be here.
So who are you and what do you do?
Well, I'm Rob Hayes, CEO of Atom Computing. Atom Computing is a quantum computing hardware company on a mission to really create the world's most scalable and reliable system so that we can help our customers reach their next big discovery.
Well, that was short and sweet. So what does that mean in a little bit more detail? What is atom-based computing and how is it different than maybe other modalities of quantum computing?
Yeah, good question. So Atom Computing is a quantum computing hardware company, like I said, which basically means we're building hardware platforms on which people can run their applications. And for us, the mission is pretty clear, which is we really just need to build bigger machines as measured by number of qubits, and we need to make sure there's error correction in there so people are getting the right answers. And there's a lot packed into that short sentence, and it's a lot of hard work. But at the end of the day, we're using a technology that will allow us to scale up to very large numbers of qubits by using the world's first nuclear spin qubit that's made out of neutral atoms. And neutral atoms are alkaline earth elements that come out of the second column of the periodic table, and they have a property that they're very kind of stable and don't interact with other atoms unless you want them to. And we're trapping these atoms in a vacuum chamber using lasers at a certain wavelength of light that allow them to get very cold and still in space so that we can kind of control where they are. And then we can read and write quantum information to them using cameras and lasers. And that's basically how we're doing it. And in order to scale up the machine to more qubits, we just simply create more spots of light, each of which are individually controllable. And we can run the gates and circuits using those types of controls. On top of that, we have a software stack, infrastructure software, and APIs and ways to program the system, as well as layering in error correction over time in order to build very useful quantum computers.
So obviously building a quantum computer with the software stack to control it is a big undertaking. Where are you on that journey? How far are you from being commercial, or maybe customers are using it today? Where are you in the journey?
Well, we're a very young company. We were only founded in 2018 and got started building our first quantum computing system in 2019. And in 2 years, we were able to build what's really was tied for the largest quantum computer at 100 qubits. And we did that with far less resources than anyone else. And that's really just a testament to the technology that we've chosen is very kind of efficient and quick to scale. So what we have is our first system. I'll call it a prototype system now. It's called Phoenix. It's 100 qubits. It's up and running. We're using it right now internally to tune it, test the software stack, get the thing feature complete so customers can use it. We'll start to allow customers to use it in really weeks, not months now. And that will start the learning curve of the software, the applications, and the hardware kind of evolving together, which is really important as we go. But to be perfectly honest, a 100 qubit system isn't all that useful. It's nice for research and running, toy algorithms, but to run real applications with commercial value, we need much, much larger systems. And that's what we're working on in the background.
How large is large? What's next beyond 100?
Today, semiconductors are billions of transistors, right? And so I'm sure someday we'll have billions of qubits as well. But the good news is you don't need billions of qubits to get value. The way quantum computers work by being able to kind of compute lots and lots of information simultaneously inside of the qubits is going to allow us to do useful work, probably with thousands or at least tens of thousands of qubits. But ultimately, we want to get to millions and beyond. And I think everyone pretty much has that same kind of idea in the industry of where we need to go.
So you're using atoms as the base modality. I think there are 3 or 4 other companies in various parts of the world that, at least at a high level, are doing the same thing. How are you different? Why are you different?
Yeah, maybe I'll kind of unpack that and answer that in 2 ways. One is why are kind of neutral atoms, or what some people call cold atoms, why are they kind of different or better than the other modalities? And then how are we different or better than other companies working in our modality. So first of all, neutral atoms or cold atoms, as they're sometimes called, basically are kind of superior to what the older modalities or the modalities that have been around longer, I should say, in superconductors and trapped ions. For a few reasons. One is they're not manufactured. We're not manufacturing chips or devices in order to build these qubits. We're basically just capturing a natural element in a vacuum chamber. So there's no imperfections because each atom is identical by nature, right? They're very stable. We've demonstrated world record coherence times of over 40 seconds for every qubit, and we've got an archive paper out in the public domain for folks to read on how we did that. These atoms are controlled wirelessly by lasers, so we can read and write the information without having to cable up each qubit. So that makes it unique from other modalities where generally on their chips or devices, they're able to get maybe a dozen or 20 or so qubits per device, but then they have to cable up all these different devices in order to get them to operate as one larger system. We don't have to do that. We just create more spots of light, and our atoms are placed, a few microns apart, which are far enough apart that they don't interact with each other in their ground state, but close enough that they can have a lot of interaction in a quantum state, and that allows us to write 2Q gates, and we can do all that in a very, very small space. So at 100 qubits, the whole system is less than 40 microns on a side, and to get to 1,000,000 qubits, we would still be less than 500 microns on a side, so less than a cubic millimeter, far less than a cubic millimeter to get 1,000,000 qubits. So it's quite unique in that way relative to the other modalities that have to be cabled up and put into dilution refrigerators and things like that. With respect to our position versus our competitors in a similar modality, on one level, we're all kind of in the same place. We've all kind of got something around 100 qubits. There's a couple other companies that are out there that are doing something similar. But in some ways, we're going after either different applications or different go-to-market. I know one of my competitors is more around building systems. I'm more and selling the systems. I'm more focused on building a cloud service at this point in time. Another competitor is building a simulation machine, not a gate-based machine. And most people believe that gate-based machines are what's really needed for the future. So there are differences in sort of our approaches, even if we're using similar technologies.
So let's talk about go-to-market. The customers that you mentioned. First, what is it that they want to do with a 100-qubit system? And how do you make it available to them? Is it through your own cloud? Is it through a cloud from like Amazon or Microsoft or one of these guys? Is it in some other way? Talk to me about that, please.
Yeah. So our 100-qubit based system is it's contemporary with the size of many of the systems that are out there. Some are dozens of qubits. There's a few that are 100 or so. And right now, most of the customers that would use something like that are classic early adopter customers that are wanting to build up their internal skill sets on how to program quantum systems and learn, kind of how does the performance differ versus CPUs or GPUs or other accelerators. And they're willing to invest in people and time in order to go get those learnings. But there's not a lot of economic value that gets created out of such small systems today. It's more like a preparation and a learning, right, for the future systems in the next 2 or 3 years. And so the kinds of companies that we're seeing that are making those investments are, large banks on Wall Street, for example, are building up, some teams to figure out how to do portfolio optimizations or risk management kind of problems that they can use quantum computing for. We're seeing a lot of interest in transportation and logistics, where we've got different mapping or routing problems that quantum computers can help with. Biotech for chemical and molecule simulations, and there's a lot of interest, excuse me, in the government space worldwide for lots of reasons, but government research, defense usages, as well as just building up sort of the economic and technological capabilities in quantum, because everybody knows it's a huge paradigm shift for the next 50 plus years in computing, and nobody wants to get behind. As far as go to market, today on Phoenix, we don't have it available on any third-party cloud. We only will offer it through our own API initially. So we'll give customers access, through through our own private cloud and let them test the code. We'll be launching our a more public cloud service in the future, but we're not ready to announce the date yet.
When you look at a quantum computer, it's a very complex system, starting from creating the individual qubits to controlling them, and so on and so on. It's a multi-level stack. Do you see yourself as vertically integrated, sort of like the car manufacturers of way back then? Or do you think that your work stops at some level and then other companies or other organizations will take care of other points in the stack?
Yeah, I think, as a hardware platform provider, we're going to need to have some skills and capabilities and know-how top to bottom in the stack so that we can understand how customers want to use the system and how it performs and help guide them. But from a business model perspective, we have much more of a horizontal building block approach where we'd like to partner with software providers and cloud service providers, application developers, and consultants and system integrators, all of the above, in order to basically participate in an ecosystem. And our goal is really just to build, like I said at the beginning, the most scalable quantum computers we can with error correction, and then let our partners invite the customers and help the customers program them to do whatever applications they want.
You mentioned that the early customers are experimenting, essentially writing toy models, because perhaps with 50 or 100 qubits, they're not going to get anything that they couldn't get done on a classical computer. At what size of a quantum computer, or what other parameters, whether it's fidelity or connectivity or gate set or anything like that, do you think that people will get true quantum advantage?
Yeah, I mean, that's the billion-dollar question you're asking right there. And I don't know that I have all the answers on what is going to be the killer app on 1,000 or a 10,000 qubit machine in the future. But what I hear from customers is there's lots of ideas on what people think that they can use, these systems of these scales for. And one of the things that we're doing, and with partners and others, is really trying to map out some of these use cases of interest that we're hearing from customers onto how many, qubits or circuit, how big does a circuit need to be? How deep does it need to be? How performant does it need to be in order to provide value versus what they could do on a classical HPC cluster, for example. And it looks like there are some early use cases that will have, economic value in the, I'll say 1,000 to 4,000 kind of qubit. But again, these will be early adopter use cases. They could be big, like big financial services ones, big pharma ones, for example, machine learning in cloud services. But as we scale to 100,000 and 1 million and beyond over the coming years and decade, I think a lot more applications are going to get written. A lot more use cases are going to fit in those class of systems or size of systems, and we're going to do everything we can with our partners to help our customers discover the next killer app that probably no one's even thought of yet, to be honest.
I think that one of the issues that people talk about is the workforce issue. I saw a slide from McKinsey, I hope I remember it correctly, that in a couple of years there will be 10,000 open jobs in the quantum computing industry, and maybe 4,000 or 5,000 people that can do it. So there's going to be a huge shortage. What do you think about that, and what do you think should be done to close that gap if it exists?
Yeah, I think it is going to be a problem. Today, the market and the kind of industry is small enough that, it's probably not it's not an immediate problem that we don't have, like millions of people that have the right skill set, but it is scarce today. And so there's definitely competition for talent. For us, what are we looking for? Number one, it's technical talent, right? Engineers, physicists, software developers, of lots of different disciplines, right? Because we're building a complete system. So, think of any engineering discipline, it's probably somewhere embedded in our system. And so we are attracting, we have over 20 PhDs. We're a small company, but we've got lots of PhDs. We're over 80% engineers. And like I said, multiple different disciplines. So we need to, in our company and the industry at large, attract talented engineers who want to come into a nascent industry like quantum computing and bring their talents to help us, make it real. And then there's also the business, the business hires and the administrative and all that. And when you're building companies in an industry, you need all disciplines as well. It's not just technical. Technical is number one. That's going to be the the majority of the jobs, but we also need, finance and marketing and business development, sales, and all the other disciplines. And at Atom, I feel very blessed that we've been able to attract really good talent. Um, we've got an amazing technical team that Ben Bloom and Jonathan King, who founded the company, started to build, 2-3 years ago. And we continue to get very high caliber resumes flying in, which is really nice. And then we've started to build the business team to go to market. We just hired Denise Ruffner, who has experience at IonQ and IBM Quantum. So she's very well connected in the industry and very talented. And Justin Ging, who we hired out of Honeywell Quantum Systems recently, and he's going to be our head of product. And he's got a lot of experience at both semiconductor companies as well as quantum systems companies in defining products that customers love. And so we're really excited to have that team on board and start building out the business side as well. I think that the next big challenge for us, in addition to just skill set, is diversity. We're not where we want to be on diversity. When you look at the applications that quantum computing is going to have, it's going to touch many different people around the world, many different types of industries, and eventually consumer life. I don't know how that'll do that exactly, but we know it will. And we want those products and services to represent the people, and we need more diversity of thought and experience and background and culture in the industry in order to discover those applications and make sure that they have great user experiences that people around the world love. And so that's something that we at Atom Computing are really trying to dedicate ourselves to, is attracting a diverse workforce. And that's going to start with education and sponsorship of interns and things before people actually walk in the door, and send us a resume. We're going to need to make sure we attract them, a diverse set of people, into the industry at large.
As we get close to the end of our conversation today, I'm wondering, as CEO, what keeps you up at night? Is it overhyping quantum computers and there'll be a quantum winter, or is it funding, or is it people? What's the thing you're most worried about?
That's a good question. A lot of people talk about this quantum winter. I don't buy it. Right? We're at the ground level of building quantum systems. We're basically we're capturing atoms and we're turning them into quantum computers. It doesn't get any more elemental than that, right? And I'm very confident in our roadmap and our team in order to go do that. And as long as we continue to scale the systems at the pace that we know we can go do, I don't think there'll be a quantum winter. So that doesn't worry me. I don't worry too much about funding, because if we execute to the roadmap, I know the funding will come. And so what I really worry about is building a team, competing for the scarce talent that's out there, attracting the diversity like I just talked about, and executing to our technology roadmap at a pace that really kind of sets the pace for the industry, to be frank. And that's what I get up to do every morning. And that's what I guess maybe keeps me up at night, is how can we go faster?
Excellent. So, Rob, how can people get in touch with you to learn more about your work?
Yeah, love to hear from potential customers, partners, employees, anyone that's interested in following our journey. You can follow us at atom-computing.com.
Very good. Well, thanks so much for joining me today.
Thank you. It was a lot of fun.